in S star, but the degree as measured in this graph, right, the residual degree after we remove everything else, it must be greater than or equal to the number of edges in this graph. Because this vertex covered is a cover for it. It's covered all the edges, so its degrees have to cover. Keep this in mind. But what this means is that if you look at the average degree of a vertex in the optimal solution, right? So this is the sum of the vertex degrees. The average degree is sum of dv divided by opt. This must be greater than or equal to right? Okay, now let's apply all these tricks we've used in the past. If you have a set of numbers whose average is at least 10, there must be one number that is at least 10. Right? You can't have an average of a bunch of things be at least 10 and have none of the numbers be 10. But the average will be less than 10. Which means there exists some vertex belonging to S star such that the degree of that vertex in G minus 1 is at least this much. Okay. Now, why is this statement important? We got through it through an indirect way. We looked at the average, we said, okay, the sum is big enough, therefore the average is big enough, therefore this one vertex has a high enough degree. Why is this interesting to us? Given what we just talked about in terms of greedy algorithms. Why would we care about this? Yeah?
Is it because it implies that your greedy algorithm must have chosen a vertex of at least that degree?
That's exactly why it's important. Because we are guaranteed that there is some vertex that has a big enough degree, whatever big enough means, our greedy algorithm, which is looking for the vertex of largest degree, has to either pick this or something with a degree even bigger than this. It can't pick anything less than this because I've shown there's something that's at least this big. Right? So I'm looking at all the degrees of... My problem with the greedy algorithm is I have all these vertices in the graph and they have these different degrees. I don't know what I was going to pick. But because I can guarantee there's some vertex that has this degree, I know that my greedy algorithm will pick a vertex of degree at least this. That make sense? And since I've made this reasoning at every step of the way, for arbitrary I, this holds true for everything the greedy algorithm does. At every iteration, it's going to pick a vertex whose degree is at least that much. Okay? Which means that if I now sum up, so let's look at the, let's sum up the degree, let's sum up, so let's think, okay, let's see that I pick vertices, I number the vertices in order of picking them. So I have vertices v1, v2, v3, and I keep picking them. This is degree 1, this is degree 2, this is degree 3, in the respective graph that I'm measuring it in. So now I can say what is the sum of the degrees of all the vertices that I pick from, let's say, I equal to 1 to some k. This corresponds to all the edges that I pulled out. Remember what I want to show? I want to show that I'm making progress. What I'd like to say that this number is big. After I've done it for k steps, I've pulled out lots and lots of edges, which will make me happy. Well, I know that by the previous reasoning, since I'm always picking a vertex of degree at least this much, whatever I pick has to have degree at least as much as this, which is at least as much as that. That's my lower bound, right there. I know that this is greater than or equal to sum of just by what I substituted earlier, right? But now since the edge size are always decreasing, I can always replace this by So notice what I've done? I've replaced this running sum by a fixed number because that ek is always less than or equal to all of these things. Right? Which just makes my life simpler because now it's a constant.
Again, just to remind me, ek is the number of edges remaining after you've taken out k vertices?
Correct.
Okay.
Correct. Okay? And I can simplify this expression as basically because now it's a constant. Because I'm just summing up a constant. Okay? Now, what is k? Well, k was I ran it for k steps. Right? Well, what is k then? Let's see. So let's set, and arbitrarily, set k equal to opt itself. In other words, pretend you knew what the optimal size solution was and run your algorithm for that many steps, therefore picking up that many things. Now your algorithm may not give you the correct answer, it may not stop, there may be edges left over. But what we can say is that so in other words, think of the number of edges remaining after you've pulled out opt vertices. If you were optimal, this would be 0. But you're not, so it's going to be something. And what we're saying is that the total degree is greater than or equal to that something. But, and this is the oldest trick in combinatorics, right, is to count the same thing 2 different ways and compare them. And then magic happens. So we've counted this one way, let's count this another way. What is this quantity here? This is the number of edges you've pulled out. Right? This is all the edges you've taken out of the graph. Okay? Well, all the edges you've taken out of the graph of G, so let's write this again. So remember we just said that sigma di is greater than or equal to E opt. But what is E opt? E opt is also equal to the number of edges in the graph minus everything you pulled out. Right? Because when you pull out an edge, you don't count it twice, it's gone. Right? You take your original graph, you pull out all the edges, what you're left with is the edges in E opt. We've counted this same quantity in 2 different ways. But now if you put them together, you get that 2 sigma di is greater than or equal to E, or sigma di is greater than or equal to E over 2. After running the algorithm for opt steps, we are guaranteed to have reduced the number of edges in the graph by at least half.
That seems terrible.
That seems terrible.
Well, you know that opt only had to run at opt steps to get all of them.
Yeah, so opt went, run steps, la la la, I got everything, and you're like huffing and puffing, and oh my god, I got halfway to go still. But less than half, no more than halfway to go. Okay? All true, all terrible, but there's always a glimmer of hope. Because that means I've made progress. You know, we shouldn't judge our algorithms, they're trying. You know, they are trying, we should be nice to them. You've done all this work and you've got halfway. The rest, you should be able to see what's going to happen. What do you think is going to happen next? Everything you've learned in the first 2 weeks of classes is enough for this. Forget approximations, forget everything, huh? Tell me, what are you going to do? So you've done all this work, you got halfway. What do you do now?
Go right on the subproblem that's remaining.
Do it again. Run all this work, you go halfway. And halfway. And halfway. How long will it take you to end?
Zeno says you'll never get there.
Yeah, but Zeno's a fool. We are discrete mathematicians, we are not continuous people. What does modern discrete Zeno say? Log n. Why log n?
Let's
do the power of n. Like, we are making half every time we take.
But how many edges do you have total?
E.
Which is at most? If n is the number of vertices, what is e? What's the maximum size of e? N choose 2. What's the log of that? 2 log n. So log n is correct, but for that reason, not because log of n, it's log of n squared, which is 2 log n. So in other words, now that we know that after opt steps, we reduce the number of edges by half, we basically have a recurrence that says that t of, let's say, I don't know, I want to talk about the number of iterations, so let's say t of I is equal to, well, let's say t of e is equal to t of e over 2 plus opt. This is a recurrence equation, right? That, let's say this t of m, which we often use for number of edges, is t of m over 2 plus opt. You should all be able to solve this recurrence. T of m is equal to t of m over 2 plus opt. You can either unroll it, you can apply the master theorem, you can do whatever you like. The answer to this is going to be you all believe that? Yeah? That if you solve this recurrence, this is what you're going to get? But what this is saying, remember, time for this greedy algorithm is the number of vertices it picks. What this is saying is that if after I've run this whole greedy algorithm for opt log m steps, my graph will be empty. And I'll be done. So even though it took me opt steps just to remove half, all is not lost because it's greater than or equal to half. And so this basically means that t of m, which is essentially the size of the vertex set we produce, divided by opt is less than or equal to log n. And I proved my approximation. So what was the intuition here? The intuition was we want our greedy algorithm to make progress. Okay. We were able to show it makes micro progress at every step by saying that there's always a vertex of large enough degree to play with. We were able to use that to show that it makes macro progress, that after so many steps, it's cut off half the edge set. We applied a recurrence bound to then say, okay, after log times that many steps, it will be done. And you get out. Questions?
So we say alpha, this is an alpha approximation, this is a log m approximation of, okay.
Yeah, alpha is log m. So when I talk about alpha, alpha doesn't have to be constant. It's just something. I mean, you want alpha to be as close to 1 as possible, but life happens. So what do you think might be the next question to ask here when you see this? Once you've understood how this is working, well, maybe I'll just stop here. Do you all understand how this is working? How the analysis is working here? Again, it's one of those things where the algorithm itself is relatively straightforward. What's tricky is proving that it does what it's claims to do. Yes.
So whenever I come up with a bound, the question I always ask is, how tight is it? Is there a way to get an even smaller? Or
Can I do better?
Yeah.
I want to do better. Can I do better? Yes. It's always a good thing. And so one question you could ask about this algorithm is, can you do better? And you can ask this question here in one of two ways. Is my analysis of the greedy algorithm sloppy? Or is my algorithm sloppy? You see the difference? It's one thing, you could take an algorithm and give a very weak bound for what it's doing. It'll be correct, but a weak, sloppy bound. And that same poor algorithm which you malign with your weak bound, maybe if you were to work harder, you'd give it a better reputation by giving it a better name. That's one possibility here. That the greedy algorithm is awesome, but we're just a bunch of fools and we haven't figured out the right way to analyze it. The other possibility is the greedy algorithm is actually quite bad. That it just cannot do any better. And right now we don't know which is the case. It turns out that we have in fact not maligned the greedy algorithm. It actually is this bad. There is a construction, you can construct a graph, and something that I hope you can think about. You can construct a graph where if you run the greedy strategy, you will in fact get an answer that's way worse. And the trick is to realize that the greedy algorithm is greedy. It's very aggressive. It always wants to do the best thing possible. So the trick in your graph construction is to sort of put a little bit of bait there for the greedy algorithm. Make it look, ooh, nice shiny vertex with large degree, and make it pick it. Whereas it could have, if it had just been a little bit less greedy and picked something that looked a little worse, that would have been much better. But because it picks that big, shiny, greedy thing, it subtracts out edges in such a way that it gets another shiny thing, another shiny thing, another shiny thing, and it keeps having to pick them. Whereas not going for the big shiny object earlier would have helped it. I will let you think about this. It's an interesting and not entirely trivial exercise. The graph you construct actually needs only be bipartite. So it's not that hard to construct this graph. Think of a bipartite graph where you have one side with the greedy algorithm picking stuff and it's covering edges on the other side. Okay? So the greedy algorithm is quite bad. And so the natural question will be, well, can you do any better with a different algorithm? But before I go there, it turns out that there's a reason, well, potentially a reason this might be bad. Often an algorithm is bad at solving a problem because it's actually solving something much harder. And so the fact that it can't solve this particular problem well only is because it's solving a much bigger problem, and that problem is actually solving quite well. In particular, let me define a variant of vertex cover, which is a bit more general. Let me define the problem of set cover. In set cover, your input consists of, so you have a universe and a collection S1, let's say up to Sm, of subsets of the universe. Okay? So you're given these subsets of the universe. You can assume without loss of generality that the sets together contain every element in the universe, otherwise you can just throw those elements out. So without loss of generality, we'll assume that the union of all the Si is equal to the universe. Okay? The goal is find a sub-collection S, let's call it Si1, Si2 up to Sik, such that the union of the Sij is also equal to the universe. In other words, we have a bunch of sets that cover a universe. Find a smallest subcollection of sets that also covers the universe, so it's less wasteful. This is the set cover problem. And again, you have sets covering a universe. I will leave it to you to ponder the question of how this relates to vertex cover. It turns out vertex cover is just a very special case of set cover. And if you think about why that might be, you'll realize that it's a very, very trivial connection. So vertex cover is a special case of set cover. Now suppose I wanted to design a greedy algorithm for set cover. What might I do? What would be the appropriate greedy strategy? Remember that my goal is to cover the entire universe with my sets. So what would be the obvious greedy strategy? Yeah?
Pick the biggest set. Pick the biggest set.
Well, yes, but let me rephrase it a little bit. Pick the set that covers the most number of elements. Because after a while I'll be covering elements up, and it's not the biggest, but the one that covers the most number of uncovered elements is what I care about. So, but you're basically right, that's the idea. So the greedy algorithm here is pick the set that covers the most uncovered elements. Repeat. It turns out that the greedy algorithm we saw before, which is of course the same as this one, and its analysis can be applied to this algorithm as well. The exact same analysis will apply here. The reasoning is that if you have an optimal solution, it covers the universe, there must be at least one set, that covers a reasonable fraction of the universe. That's the one you're going to pick, or something better, repeat. After a while, you make progress and you're done. So the greedy algorithm we saw before gives you a log m approximation for this problem as well, which is actually in some ways harder than vertex cover. Again, if you think of how you reduce vertex cover to this, you'll see what is more general about this. It has something to do with the sizes of the sets. So the greedy algorithm is good for this, and again you can ask the question, well, is the greedy algorithm really good? Can you do better? It turns out for set cover you can't. For set cover, in fact, this is the best thing you can do. In fact, you can say the following, that so small O of log n, so strictly less than log n. Or in other words, finding a small O of log n approximation for set cover is NP bar. Set cover, by the way, itself is NP bar, finding an exact solution. Okay. We'll see later on how to prove statements of this kind. It's actually quite interesting. But for now, just take it on faith. So the greedy algorithm is great for set cover. You can't do any better. There are small things you can adjust, but basically that's all you can do. So our situation is we have set cover and we have vertex cover. We have a greedy algorithm, which is log n here and is log n here. And this is tight, this is not. So if we are going to hope to get a better algorithm for vertex cover, we need a different strategy. We need a different approach altogether. Okay. We might need to look for a different lower bound reason. Okay. And so the question is, what might that be? Let's think about our graph again. So I'm going to draw a different graph because I can't really look at the graph. I don't even know how to do it. Let's look at this graph for a bit. And I'm going to mark off two edges in this graph. I'm going to mark out this edge. And I'm going to mark out this edge. The interesting thing about these two edges, the reason why I marked them off, is that they are disjoint from each other. They don't have any overlap. Think of your optimal vertex cover. It has to cover these two edges, right? Yes? But can it cover them with less than two things? No, because these edges are disjoint. You need at least one vertex for one of them. You need at least one vertex for the other one. Right? In other words, right? Do we have a name for a collection of disjoint edges in a graph? Have we maybe seen such a beast before? Yes? What is it called? Have you seen it before? Where have you seen it before?
No.
Which homework?
Independent set.
Sorry?
Independent set.
No.
Right? Right?
Sorry?
Flow.
You saw the flow homework, right? Somewhere.
Yeah.
Okay, but what was it called? We want to find a maximum collection of disjoint edges.
Min maximum.
That's a min cut. That's not this. These are disjoint edges. A min cut can have lots of things overlapping.
Oh, was that the one with the escape path?
No. Now you're all flailing violently. So I applaud your efforts, but it's it's not really going anywhere. So. Matching? Maximum matching? Pair of roommates, remember? Reduction from flows? Yes? You know this will be the final one. So the size of vertex cover is the size of a collection of disjoint edges, aka a matching. But I didn't say what this matching is, it could be any matching. So in particular, we have a lower bound. Maximum matchings we know how to compute. We can do that. This gives us a lower bound. That's great. What it doesn't do though is give us an algorithm. So I can compute my maximum matching in my graph. Okay, all these edges are pre-covered. Fine, I cover them. But now what? There might still be other things that I need to worry about, right? It's not clear that, could it be that the size of the vertex cover is equal to the size of maximum matching? Could that be possible in a general graph? Is that likely to be true? What weird thing would happen if the size of vertex cover in a graph was equal to the size of maximum matching? What implication would this have? What implication would this have for your bank balance in particular? Can we compute a maximum matching in a graph? We've actually talked about this, how do you compute a maximum matching in a graph. We've seen from bipolar graphs, but you can compute a general graph. In fact, this was the first polynomial time algorithm. If we can compute a vertex cover that's equal to the size of maximum matching, it's always the same thing, and we can compute a maximum matching in polynomial time, we've computed a vertex cover in polynomial time, haven't we? We've solved P equal to NP. Someone here has got $100 million. So, we're not going to be that lucky. In particular though, and this is a nice theorem due to Koenig from many hundreds of years ago. If you want to compute a vertex cover in a bipartite graph, it's exactly equal to the maximum matching. In general though, it's not. So we made some progress towards getting potentially a better bound vertex cover in terms of a maximum matching. That doesn't yet give us an algorithm. Let me give you an algorithm. Here's my new algorithm for the vertex cover. It is the anti-greedy. We'll call it the slacker algorithm, or the stoned algorithm, if you want. Basically, the algorithm walks up to the graph and says, hey, here's an edge, takes it. Then looks up and says, oh, here's another edge, takes that one. And every time it takes an edge, it takes both the endpoints of the edge. That's it. So, the new algorithm is take any, and I'm going to underline this 3 times, so 4 times, any edge in E, let's say is equal to UV, add to my set that I'm building up, remove all edges adjacent to U comma V, repeat. So this is a totally chilled out algorithm. It just takes any old edge, cleans it up. Takes any old edge. I claim this is going to be way better than greedy. In fact, I claim that this is a 2 approximation to vertex cover. Not log n, 2. And we're going to use this idea about matchings to help us prove this. So first of all, do you agree that what you will produce is in fact a vertex cover? That it correctly covers all the edges in the graph? Why is that? Well, I took an edge, I take both endpoints. And so when all those two endpoints will clearly cover all their adjacent neighbors. So I can safely remove those things. At the end, I have only safely removed edges. So if I removed an edge, I guaranteed it's covered. When I have no edges left, everything is covered. So what I have is a valid vertex cover. The only question is it too big? The next thing you have to ask yourself is, what is something special about these edges I'm picking out? Can I say something interesting about these edges my algorithm keeps picking? So if you go back, let's actually go back a number of steps here, and I'll color them in, let's say, in blue this time. Oh, maybe I'm in blue. Green. Let's take an edge. I don't care what edge it is. I take this edge, and then take both these endpoints. And then I remove everything adjacent to them. Okay? Now I take some other edge. I don't know, this edge. Right? Take both those endpoints, remove everything adjacent to them. Now I take this edge and remove all those endpoints and I'm done. So my total score is 6 because I've taken both endpoints. It's much worse than the 4, right, in this case. But look at those edges. What can you say about them? They're all disjoint. Why is that? Because when I picked an edge, I removed all adjacent edges from either of the endpoints. The only edges left have to be disjoint to the one I just picked. In other words, all edges picked are disjoint. Okay? Suppose I pick k edges. If I pick k such edges before my algorithm finishes, how many vertices will I be picking? 2k, right? Because each edge has 2 vertices and I take them both. So the algorithm cost is equal to 2k. But these edges form a matching. And what did I say about matchings? K is my lower bound. What can we conclude from this? I have 2 approximations. So by observing that there is a nice lower bound on opt, the size of a matching, and being clever enough to design an algorithm that exploits that fact, we get a much better approximation using a much simpler algorithm. It's not even greedy. Yes?
Remind me why opt was at least k.
Okay. We agreed that all the edges picked are disjoint, and there are k of them. So they form a matching of size k. Not a maximum matching, not even, just a matching of size k. Right? Okay. Remember what he said? If you have disjoint edges and there are k of them, whatever your optimal solution does, it has to hit each one of them. So the size of vertex cover is at least the size of any matching. It's also getting the maximum matching, but it's the size of any matching in particular. So that k is our lower bound that we can refer for our algorithm. So remember how I said, right, the blueprint for any approximation algorithm says, find a lower bound on opt, relate your algorithm to the lower bound. And that's exactly what we did. Put those two things together, you get your bound. But we had to be more clever here. we had to use special structure of the vertex cover problem, of graphs, of edges. This notion of edges and matchings and disjoint stuff doesn't quite work for sets. And that's good, because we know that for sets you can't do this trick. It's going to get much worse. You can do something like this, but the approximation you get is different. It's not going to be 2. It's going to be basically the maximum number of vertices in a particular set, which could be very bad. It could be n. So, but this works specifically for vertex cover for this reason. And we get this one. Now you could of course ask, well, can I do better than 2? Because 2 is okay, but it's not that great. And the answer is no, we don't know. We don't think you can. But we're not sure. All we know is that you can't do better than, I think, something like 1.16. To get better than 1.16 is NP hard. But we don't know if you can get better than 2, and there's some separate evidence that I will not discuss here that suggests it will be very, very difficult to get below 2. But it's not the same as, well, we just don't know. But that's where things stand. That's part of what this is. And this really very simple strategy is what does it. Okay? Questions? So once again, while the basic template is the same, find lower bound, relate out to lower bound, the specific nature of the lower bound you produce and how good you are at doing lower bounds will control how good your final answers will be. And a lot of the sort of cutting edge research in approximation algorithms is all about trying to find cleverer and cleverer lower bounds to get better and better approximations. So it's very, very complicated. This is not, I would not expect you, on say a homework assignment, to be able to get, all the way to the best answer. All you want to be able to sort of think about is how to design some lower bound that gives you something. Yeah.
What's an example of a real world problem that is solved with vertex cover where the NP hardness comes into play?
What do you mean comes into play?
Meaning that the size of a realistic problem that I'm trying to solve is so large that it's going to take too long for an exact solution.
I don't know if vertex cover itself has any good sort of real life examples. I think vertex cover and I've spent, you'd be surprised how much time I've spent in grad school trying to track down sort of real world examples of vertex cover. I don't think there are any. I mean, it's an intuitive problem in graphs, but I don't think the real world applications, as far as I know, are that compelling. But there are many others, like for example, set cover. Coverage problems come up very often. You have a certain limited set of resources and you want to cover some space. How do you plan? And that comes up all the time. The problem we're going to see next, which is the traveling salesman problem, is again something that comes up all the time, finding the routes for things. The make span load balancing problem, that comes up all the time. Schedule. So a lot of these questions come up all the time. And yes, the NP hardness becomes an issue because now you can't really solve these problems exactly. Now there's always a trade-off, right? How much time you have and how good you want your answer to be. There's always a trade-off between them. If your problem is small enough, maybe just do a brute force. If your problem is really huge, use an approximation. But there might be a region in the middle where you spend more time than the simple approximation gives you, and you get a slightly better answer. So in fact, there's a whole, and again, I can't talk about this in this class, but there is an entire continuum of results that say things like, well, 2 is very fast, exact is very hard, and there's a whole spectrum in the middle where you can spend a certain amount of time that's not polynomial, but is close enough to polynomial that you can still get an answer. And there are bounds for that as well. So there's a very smooth trade-off for many problems, not for all, but for many problems you can get these trade-offs. For many problems you can get polynomial time trade-offs, that you just get better and better accuracy, but it's always polynomial time. And we'll talk about that as well. Okay? In the next lecture. So so I'm just giving you a teaser for the basics of how to think about approximations. This is by no means the complete story of what people have actually done. So for example, when we talk about linear programming, we'll spend some time talking about this. Using linear programming, you can get better and better lower bounds in the problem, just by adding more and more constraints to your linear program. And then, there's people in operations research do a lot of this kind of work. Where you frame the problem in some abstract way, just throwing in constraints, you get better and better answers to your problem. So there's a huge sort of industry and theory around getting good approximations for problems that you can then use in practice. And again, the goal is you want provable guarantees. If you don't want provable guarantees, you can do whatever you like. And there's also lots of good heuristics you can use. But it's important to often be able to say, look, I know I can get to the next, no matter what I do. Okay. So, I want to switch gears a little bit. I've been sort of saying, oh, we can get these good approximations and all so on, and I'm hinting at, oh, well, there are limits to what we can do. I want to give you a simple taste of how you can show that there are limits on what you can do. And I think there's an interesting philosophical underpinning to this question of why should there be limits on how closely you can approximate? After all, you're not getting the exact answer, you're only getting close. Why should it be okay to get close? And the next problem I'm going to look at will show you why this happens and why there are so many problems for which not only can't you get a good answer, you can't even get close to a good answer. And the one I'm going to show you is the worst, like this, the poster child for how bad this can get. And it's traveling salesman. So recall, you have this traveling person going around a country or somewhere, just sort of delivering things. Like your UPS driver, you can think of it like a postman, anyone you want, person. And so the abstract problem is the following. I give you a whole bunch of destinations. And you can imagine that there are roads connecting all of them. In practice, maybe there aren't, but in general, imagine there are roads connecting all of them, right? And each road has a certain length. So there's an E, there's an L and E. And your goal in this problem is to find some kind of path. I hope I can do this. Right? And maybe if you want, come back to the beginning. That visits all the locations and spends as little effort as possible doing it. Where here effort could be distance traveled, whatever you want it to be. There's some measure of effort per edge. So the easiest case, think of the length of an edge. So you want to spend as little distance as possible doing this. And of course, this problem is NP hard. We've seen an example of this reduction. And in particular, if you had to actually look over all possible ways of doing this, you'd be spending n factorial time because there are n factorial permutations of the vertex set. You really don't. So what you'd like to get is an approximation.
Does this problem allow, or so it's kind of a graph problem, right? Does it allow you to traverse an edge that you've already traversed?
Yeah, you can do what you want.
Okay.
It just would be wasteful. If you ever traverse an edge you've already traversed, then probably there's a shorter way to go around it. Maybe.
Well, maybe that destination is isolated.
No, sorry, you can't traverse an edge you've already traversed because you have to visit every location exactly once.
Oh, exactly once.
Sorry,
Okay.
you cannot traverse an edge.
Okay.
So it's important that, yeah, you want to traverse every location exactly once. Right, so visit. So unlike in the case of exactly once. So you might be asking yourself, isn't this the Hamiltonian path problem? It is and it isn't. It is because you have the same idea of visiting everything exactly once. It isn't because in the Hamiltonian path problem, you just have an undirected graph, all edges are weight 1. You just want to find a path. So all paths have the same cost, n minus 1. Here, you want to find the shortest one. So it's a little bit different. But that intuition is very important because we're going to show that, we're going to show the following here. So fix any function that can be computed in polynomial time. So talking about a function that can be computed, not a function that is polynomial time, a function that can be computed in polynomial time. So in particular, e to the n can be computed in polynomial time. So this function class is a very big class. this is like, go away. Nothing's happening there. You pick whatever function you want to approximate it. It's like, please, 10% log n, 2 to the n, 2 to the 2 to the n? No, you cannot do it. This is like, there's bad news and then there's bad news. So again, what I want to impress upon you is how horrible this result is. How depressing it is. And then I'm going to prove it. Which will make us be a little bit happy. Okay, so what this is saying is that all this 2 log n nonsense you're doing, don't even bother wasting your time. You can't do anything. There is no hope. And now let me prove this. And I'm going to use Hamiltonian. So remember, the Hamiltonian path problem starts off with a graph, an undirected, unweighted graph, and merely asks, is there a path to go from one to the other? What I'm going to show you is a reduction from Hamiltonian path to a Fn approximation for TSP. Okay? Such that any approximation for TSP gives me an exact answer for Hamiltonian path. Okay? I have therefore then proved that an Fn approximation for TSP is NP, because it would give me a solution for. That's my plan. Okay? So you see the meta plan, right? If I can show that the solution, exact solution, which is the yes, Hamiltonian path is a yes, no problem. Is there a path? If I can reduce this yes, no problem to this finding some approximation for TSP, then I've shown the theorem I want to show. But to keep it simple, let's make Fn very simple. Okay? So let's make f of n something like 2. Or rather, let's make f of n even simpler. Let me just do a construction tree. We'll see what happens. So I start off with a graph, and I have to go to some complete graph with weights on edges. Right? That's what an instance of Hamiltonian path is, a graph. An instance of TSP is a complete graph with weights on edges. What should I do? Well, here's my rule. My rule says that the length of an edge is equal to 1 if the edge belongs to G, and it's 2 if the edge does not belong to G. Okay? Is that fair? So this gives me a correct reduction from G to the complete graph with weights on edges. I should say, I should call this L. Since I'm also using L here. Right? So I have a valid reduction from an instance of Hamiltonian path to an instance of TSP. What I need to do now is figure out what my thresholds are, right? So suppose I solve the TSP, I get some answer. How do I tell if this answer is a valid solution to Hamiltonian path? Anyone? How would I know? So I run my TSP, I get some answer. Is there any way to tell immediately, looking at the cost of the answer, whether it's a valid solution for Hamiltonian path? So when would a TSP solution also be valid for Hamiltonian path? If I only, remember, I've added a bunch of extra edges, right? And I've given them a different weight for edges that weren't in G. Yes?
If the length of if the total cost is exactly that, the reverse is number.
Exactly. If the TSP cost is equal to n minus 1, then this must imply that there exists a Hamiltonian path. If the TSP cost is greater than or equal to n, this must imply there is no Hamiltonian path. So do you see why? Because if I only used edges from the original graph to form this path, then each of those edges has cost 1. There are n minus 1 of them, that would be my cost. If I used even one edge that is not in the original graph, and I was forced to, because there was no other way to get an answer, then I have one extra unit of cost. I still have n minus 1 edges, but one of them has one extra unit of cost, so my cost is going to be at least n. Okay? So I can tell the difference between having a Hamiltonian path and not having a Hamiltonian path by looking at the gap between the solutions. Right? So this is called a gap. Now what I want to do is, well, so what is this saying? Think of this the other way around. It's saying, if I have an algorithm that can tell whether the TSP solution is n or n minus 1, I'm not sure which one it is, but I can tell if it's more than n minus 1 or less than equal to n, then I can decide the Hamiltonian problem. In other words, let me write this out. Suppose there exists an algorithm that, given a complete graph and weights, can tell whether either TSP is greater than or equal to n, or TSP is less than or equal to n minus 1. Then this algorithm solves Hamiltonian path. This algorithm is not computing the TSP optimally, but it's giving you some rough answer. And that's enough to solve it. In other words, some kind of approximation for TSP will give me an exact answer for Hamiltonian path. So some kind of approximation for TSP is NP. I have created a gap. Now this is a very small gap. This is not going to give me the theorem I wanted. That was saying no multiplicative approximation exists. I can't get a multiplicative approximation from this because n and n minus 1 are within a 1 minus 1 over n factor of each other. That factor goes to 0 as n goes to infinity. It's not a real factor. I would like a 2 or something. I would like to be able to say that if this is 2n versus n, then I have a lower bound. But now let's go back to our construction. Why did we choose these edges to be 1 and 2? Was there any reason? No, we just made it up to make some difference. Right? Suppose instead I said that my new L is equal to 1 if E belongs to G and is N if E does not belong to G. Okay? I allow you to do this reduction. I can put whatever weights I want on my edges when I construct my reduction Hamiltonian path to TSP. Now what can we say? If the TSP is n minus 1, as before, there's a Hamiltonian path. If the TSP is not n minus 1, what's the next number it can be? One of those edges gets replaced by something of size n. So the TSP becomes we take off a 1 and we put an n. So now we have a situation where either the TSP is very small or it's very big, by a factor of 2. This means no Hamiltonian path, this means Hamiltonian path. Okay? Suppose I had an algorithm that could say get me, I don't know, a 1.5 approximation to the TSP. That algorithm has to be able to tell the difference between this and that. Right? Because these are factor 2 apart. So imagine this. I'm asking you questions and your answers you give me are either 2 or 4. Right? I'm giving you boxes of numbers. I'm giving you a box of coins. Okay, it's a black box. And you can say, I can estimate the total value of the coin. And I prepare boxes that either have 2 coins in them or 4. And I give them to you. And you promise me a 1.5 approximation to the correct answer. You have to give me the correct answer every time. You can't afford to make a mistake because these numbers are too far apart. If you make a mistake, you could be way off, much more than the 1.5 that you promised, or the 1.4 or root 2 or whatever you want. Okay? In other words, if I create this set of instances that have a huge gap between the right answer and the, one answer and the other, any algorithm that claims a good approximation has to be able to tell them apart. Otherwise, it's not actually giving you a good approximation. And so, what I've now shown is that with this construction, I have an algorithm that now, if it can tell the difference between 2n and n, will solve the Hamiltonian path problem, therefore getting a 2 approximation to TSP is NP. I could do this again. If I do this, same reasoning applies, getting a 3 approximation is NP-hard. In general, if I replace this by any function of n that I wanted to, I can show that distinguish between an Fn approximation and getting an Fn approximation algorithm for TSP is NP-hard. Essentially what I've done is I've taken satisfiable, not satisfiable, having Hamiltonian path and not, which is basically a 0-1 problem, and blown it up into this huge gap. Either my instances have a huge cost or a very small cost. Right? So you've taken this problem where you have HP or no HP, we'll call this a 0 and a 1, and we've blown it up into either a solution of cost f of n or n. Any algorithm that can tell the difference between these two will also tell the difference between these two. And this is called a gap. And so for many problems, you can show, using these kinds of tricks and more complicated versions of these tricks, that even approximating a problem up to some level is NP. Because if I could get even a decent approximation to the answer, I would solve this problem. So this is in the notes, take a look at it. It's this idea of lower bounds on approximation via gap reductions is a little tricky. When people first started doing them, it sort of opened up a whole revolution the way we think about approximation algorithms. So it's a tricky concept. So ponder this. All is not lost with regards to TSP. It turns out that in order to do this kind of thing, you have to really mess up your distances between edges. Any realistic instance is not going to have those kinds of distances. And once we throw in an idea of what is a realistic distance measure, you can suddenly do a lot better. You can get a small constant factor approximation. So the some of this addresses your point about realistic instances. The trick is to say, okay, if I don't make any assumptions on my input, what goes wrong? Well, this goes wrong and we're dead. But if you now say, well, let's make some plausible measurement, like distances are like roads, right? Okay, roads have certain rules of what distances can be. You can't have arbitrary distances. In that case, things become a lot better. And you can do a lot, and you can prove it. That's a good problem. And so we'll look at that next week. Okay? All right, see you next week.